So last time we looked at the monotone convergence theorem, which said that if you have a sequence of non-negative monotonic functions, monotonically increasing sequence of functions, such then you have, and so fn goes to f, and then you have integral f d mu over x is limit n tending to infinity integral fn d mu over x. Okay, so this is a very simple theorem to apply. You need a monotonically increasing sequence of non-negative functions and then you are through. Of course, as I said, both sides could be infinity, and if one side is finite, then the other side is finite and the two are equal. Okay, so next we have a similar result based on the monotonic theorem. Again, a very useful result. This is called Fatou's lemma. So x s mu measure space and fn non-negative sequence of measurable functions. Extended, real valued, of course. Then integral over x lim inf n tending to infinity fn d mu is less than or equal to lim inf n tending to infinity integral over x fn d mu. Okay, so recall lim inf is what? Lim inf n tending to infinity. This is nothing but the sup over all n inf over all m greater or equal to n fm. Okay, so this is lim inf of okay, and this always exists. Okay, so given non-negative functions, so you have this inequality. So let us proof set gn equal to inf of I greater or equal to n of fi of x. Then of course gn is measurable, non-negative, and gn is increasing. Okay, gn is increasing because you are taking infimum over smaller and smaller. So gn plus 1 will be I bigger than n plus 1, so it's a smaller set, so the infimum will go, and then this increases. And what is the limit of these things is precisely by this definition which I have written here. We have that this is increases to lim inf fn n tending to infinity. Therefore, by the monotone convergence theorem, you have that integral over x of lim inf n tending to infinity fn d mu is nothing but the limit of n tending to infinity integral over x gn d mu. So this is nothing but the monotone convergence theorem. But each gn is less than or equal to fi for all I being less than greater or equal to n. So this is less than or equal to limit n tending to infinity inf of I greater or equal to n integral fi d mu over x, and this is precisely equal to lim inf of n tending to infinity integral over x fn d. So this is also equal to limit n tending to infinity inf m greater or equal to n fn, because it's an increasing sequence, so sup and lim are the same. Okay, so this proves Fatou's lemma. So example, strict inequality possible in Fatou's lemma. So So let us take x equal to r equipped with Lebesgue measure. Okay, and then you set Fn equals chi of n plus 1. So then Fn of x goes to 0 as n tends to infinity. Because this function is 1 on the interval n plus 1, and n becomes large, any x will be overtaken, and therefore Fn of x will ultimately go off to 0. Therefore lim_inf Fn equal to 0. So you have 0 equals integral over r lim_inf Fn dm1. Okay, but if you look at the integral over of Fn over r dm1, this is the integral of the characteristic function. This is nothing but the measure of n plus 1, and that's equal to 1, and therefore this is strictly less than 1, which is equal to lim_inf integral Fn dmu. It's a constant sequence, and therefore lim_inf is the same. So you have that it is possible to have strict inequality in Fatou's lemma. So next proposition is a variation of the monotone convergence theorem. So excess mu measure space Fn sequence of non-negative extended real valued functions for all x in x. Assume Fnx converges to f of x and 0 less than or equal to Fn x less than or equal to f of x. So this is unlike the monotone convergence theorem. There also we had convergence to f of x, but here we had Fnx increases to f of x. Now we are saying no, Fnx is just bounded above by f of x, that's all. So even then, so this implies limit n tending to infinity integral over x Fn d mu equals integral over x f d mu. So the conclusion of monotone convergence theorem is there. So if you have non-negative functions, either you are monotonically increasing or all of them are bounded above by the limit function. That is important. Then also you can say, so proof. So you apply by Fatou's lemma, you have that, so integral of f d mu over x is the same as the integral over x of lim_inf Fn, because Fn converges to f, and that is of course less than or equal to lim_inf integral over x Fn d mu. This is Fatou. But Fn is less than or equal to f for all n, and therefore this is anyway, sorry, that's not needed right now. This is always less than lim sup and now you use the fact that Fn is less than or equal to f. So the integral Fn is less than or equal to integral f. So lim sup Fn will be less than lim sup integral f. So this is less than or equal to integral f. And therefore you have that integral f is less than lim_inf less than lim sup less than integral f, and therefore this means that lim_inf integral Fn equal to lim sup integral Fn equals integral f d mu, and that's exactly the conclusion of the theorem. When lim sup equals lim inf, that is limit integral Fn d mu over x equals integral x f d. And that proves the theorem. Okay, so earlier we showed that if phi is a non-negative simple function, implies nu e, the indefinite integral, namely integral over e phi d mu, defines a measure on S. So now we are going to generalize this result in the following proposition. X S mu measure space, F non-negative extended real valued measurable function, define nu of E equals integral of E f d mu for every E in S. Then nu is a measure on S, and if G is any extended real valued non-negative measurable function, we have integral over x g d nu. So we are integrating with respect to nu. This is like the substitution in ordinary integration. So this is equal to integral over x g f d mu. So this is like you are making nu e change of variable kind of thing. So nu e equals integral f d mu, then d nu is equal to f d mu. Okay, so often we write this in the following fashion: d nu equals f d mu. Okay, so this is, I put it in inverted commas because this is just a symbolic notation. What we mean is, for every function g, we have g d nu equals integral g f d. Okay, so proof. So clearly nu of phi is 0 and nu is non-negative. Therefore we have to check. So E equals union EI, I equals 1 to infinity, EI in S, EI disjoint. Okay. So now let us, then what can you say about chi of E? Chi of E is equal to sigma I equals 1 to infinity chi of EI. So now if you take nu of E, that's equal to integral over E f d mu. And that's equal to integral over x of f chi of E d mu. That's equal to integral over x sigma I equals 1 to infinity f chi of EI d mu. But if you have non-negative functions, then we already saw that the summation can come out. So this is I equals 1 to infinity integral over x f chi EI d mu, and that's equal to sigma I equals 1 to infinity integral over EI f d mu, and that's equal to nu sigma I equals 1 to infinity nu of EI. So this implies that nu is a measure. So now we want to establish star. So now this is the proof technique which we are going to use. Is a very powerful one and very useful one. So this is something which you should learn very well. Okay, so assume G equals some chi f, f in S. Then integral G d nu over x is nothing but nu of E, because nu of f. Which is equal to integral over, okay, let's take chi of E, E in S, so that I won't make mistakes. Okay, so this is integral over E f d mu, and that's equal to integral over x f into chi of E d mu, which is integral over x f g d mu. Okay, so star okay for characteristic functions. Now you take f equals sigma I equals 1 to k alpha I chi of ai in S and alpha I greater or equal to 0. Okay, then we know that if you have a finite sum of non-negative functions, then the integral of the sum is the sum of the integral, and alpha can come out, and therefore integral G d nu over x this is G is equal to sigma I equals 1 to k alpha I integral over x chi of ai d nu, and that we just now saw is equal to sigma I equals 1 to integral over x sigma I equals 1 to k of f times integral x f g d mu. Okay, just be by step 1. So okay for non-negative simple functions. So now G greater or equal to 0 measurable. So there exists phi n simple, 0 less than or equal to phi n less than or equal to G, and phi n increases to G. Okay, so integral over x phi n d nu by step 2 is nothing but integral over x of f phi n d mu. Now phi n increases to G, non-negative function, so by the monotone convergence theorem, the left hand side is nothing but integral of G d nu, and that is equal to, again, f phi n will then increase to fg because everything is non-negative, and again by the monotone convergence theorem this is equal to integral fg d, and therefore this establishes the theorem. So this is a very important powerful technique, like a proof machine. You prove something for characteristic functions, use linearity, prove it for simple functions, use a suitable limit theorem like the monotone convergence theorem to prove it for an arbitrary non-negative function. Now if you want to do it further, we haven't come to arbitrary functions as yet, but in general you know how the proof will go, because if you take an arbitrary function, break it up as f plus and f minus, for each of them you prove it, because you know you can do it for this, and then take the difference. So that will be the idea. So this is a very nice proof technique which you have. So as I said already, so we have said if the indefinite integral nu could be written as f d mu, that means integral g d nu equals integral fg d mu. Now when can you do so, and you have nu of E equals integral f d mu over E. So given two measures mu and nu, when can you write this? Does there exist an f? So given nu and mu measures, does there exist f such that double star is true? So this is the content of the Radon-Nikodym theorem. When can you do this? We will see that much later in this course. So this is a particular case which we have seen. Okay.